earthquakes. All right, so what is an earthquake? Well, it's a rapid movement of the earth, and really it's actually, it seems like a rapid movement to us, but in reality, all it is vibrations that are traveling through the earth. And they can have, it's a result of displaced rocks. So it's the fact that these rocks had so much pressure building up, that all of a sudden they moved and it caused those vibrations, which causes an earthquake. And it's a release of energy. So what it is this energy is released by the earthquake that travels through the earth in these forms of waves. Those vibrations are actually waves. So a seismograph is actually the instrument that's used to detect the seismic waves that earthquakes create. So what they usually do is they have this machine this is a very simplistic version of it, but basically is they'll embed something into the bedrock, and this little elbow thing right here has a pendulum basically kind of hanging off of it. So when the earth starts to move underneath it, this little ball with the pen on it stays in one place, and it actually can get readings. And there's this paper that continuously will move through. Really, now that they have these special machines, and it has a free swinging needle pen type thing, and it will constantly, the paper runs under it constantly to see if there are movements in the ground at that point. These are also some older versions of it. This one actually can tell if the ground is moving side to side. This one can tell if it's moving up or down. So those are seismographs. Those are the instruments that measure the earthquakes. A seismogram is the paper that all of the earthquake information comes out on. It's the record sheet to use to measure, used on a seismograph. Okay, so there's multiple different types of waves. The two main ones that we're going to talk about, first one is a P wave. P waves are primary. Primary means first, okay? And these primary waves are compressional, meaning that they push back and forth on each other, okay? These are the fastest moving ones, and they also can go through solids, liquids, and gases. So primary waves, fast, solids, liquids, and gases, and they are compressional. You need to know all of those things for P waves. Then we have S waves. S waves all have S things that go along with it. So S stands for secondary, meaning it comes after the P waves. Then it has shear, so it has this side to side motion, and it has a slower velocity, and it only can travel through solids. So to remember S waves, they are slow, secondary, and shear, okay? I should have said that wrong. S waves are secondary, they're slow and shear, okay? So these are some different diagrams of how the P waves and S waves work. So P waves, they're compressional, they're moving by pushing each other back and forth, where these S waves kind of move in a side-to-side motion. And then the third type of wave is not one that we commonly talk about. They're surface waves. They're also called L waves. These ones usually it says they're produced by P and S waves. They roll like ripples on a pond, so it's kind of a combination of the P and S, of that compressional and the shear movement, only it kind of goes up and down like that. It has the slowest velocity, and they only travel on the surface, and sometimes these can be the most dangerous ones because it moves the ground so much. It can move houses and roads and bridges to the point where it really is destructive. Okay, so you need to know what a focus is. No, it's not the focus that you need to have when you're working on this kind of stuff, but a focus is the point on the fault plane at which the first movement occurs. So the focus is the part that's deep underground usually. The focus is where the earthquake actually happened. And then right directly above the focus on the surface of the land, that's where we consider the epicenter to be, okay? So the focus is deep underground where the earthquake happened. The epicenter is the point directly above the focus. So on the Moho, or the Mohorovicic Discontinuity, this was discovered in 1909 by a man named Yugoslav. He was by the Yugoslav seismologist, by Andrija Mohorovic, and he discovered that the Moho is the boundary between the crust and the mantle, and the boundary was discovered by the change in the P and the S wave velocities. So we realized that the P waves kind of were deflected and turned, and the S waves just stopped, because S waves can only travel through solids. So if they just stopped, it must have hit a liquid of some sort. And if P waves get deflected somehow, or they get moved, they're refracted, they're bent, that means that it must have run into a liquid as well. So there's this area called the shadow zone where the P waves are deflected and the S waves don't show up at all. So the shadow zone is this wide belt around the Earth on the side opposite the focus of the earthquake. The cause of the shadow zone is Earth's outer core, because the outer core, solid, liquid, or gas. The outer core is a liquid, good. So P waves are refracted, which means they're bent, and S waves cannot travel through the outer core. So at 102 and 142 degrees away from the focus, the earthquake can't be detected. So there's this open area right here that's called the shadow zone. As you can see, these P waves, once they hit the outer core, they get bent, they're refracted. So this area kind of opens up over here. That's the shadow zone, where none of the vibrations from the earthquake are felt. Okay, so how we measure earthquake, there's two different scales. We have the Richter scale, and this one measures energy. It measures the amount of energy that's given off by the earthquake. This is on a scale from 0 to 10. The Mercalli scale is measures of amount of destruction. So Richter can basically be the same. However, Mercalli scales, if they're measuring the destruction, they're going to be different on where you live. If you live in a high populated area where there's cities and lots of buildings and lots of stuff going on, the Mercalli score could be much higher if your Richter scale was only 3. So say you're in the middle of a field and you had a 3 on the Richter scale earthquake, you're gonna just feel vibrations. Whereas if you were in a city during a 3 on the Richter scale, it might have caused some destruction that you might be like about a 3 or a 4 on the Mercalli scale. Okay, so why is Richter better than Mercalli? Because Richter measures the energy, and that's going to be the same throughout, whereas Mercalli, with the destruction, like I said, it's going to measure it, and it's going to be different where you live, how many people are there, what kind of buildings and infrastructure, stuff like that. So Haiti versus California. In Haiti, many years ago, there was a really bad earthquake. It was actually less of an earthquake than there was in California. The Richter scale was much lower, but in Haiti, their infrastructure is very weak. What they make their buildings out of is very weak. So there was way more destruction in Haiti than there was in California, when California even had a stronger earthquake. But because we've learned over the years that the infrastructure they need to build in their buildings, they build them with reinforcement out of materials that can move and sway and can take the earthquake a little bit better. So the epicenter location from the stations, your P wave travels faster than the S wave. So the P waves are going to show up at stations first, then your S waves are going to show up at the stations. So it makes it possible to actually figure out the location or how far away the earthquake was based on the time difference between when the P wave showed up versus when the S wave, or until the S wave showed up after. And you need at least 3 stations. That is a magic number. 3 stations you have to have, no less. You can have more, but you can't have any less than 3 stations in order to figure out where your epicenter is. Why? Well, here's your recording station, okay? The earthquake could be anywhere on this circle. That is a lot of space to follow, okay? So what we want, if we add another circle, it kind of narrows it down a little bit. So this is our second station, and the earthquake can be anywhere in between this little funky shaped oval type thing. But if I add a third station, my third station actually gives us a pinpointed location of where the epicenter will be. So there's these 3 earthquake stations that measured the distance away the earthquake was, and we checked all 3 of the radius around them, and that's where our epicenter is going to be, where all 3 of those circles meet. Sometimes your circles will not always meet. When they don't meet, sometimes it will make a very tiny triangle right here. Inside that triangle is where your epicenter is going to be. Okay, oh, there's a there's an example of what the triangle would look like. Okay, the next section is figuring out the distance and the times and all of that stuff. I'm going to do a different video for that because that's going to take a really long time, and some of you are going to want to look back and watch that, so that's going to be in a different video. So this was the intro to earthquakes.